Hey everyone, so this is problem set 5. Just like last time, this is going to be up on Canvas, so you can actually work on the problems then. And then you can input your answers. If you don't want to watch my explanations, feel free to just skip ahead and just input your answers. Otherwise, it is kind of recommended that you try looking at some of them, especially the ones you get wrong. But you never know, I may make a comment in going over a question you got right that kind of relates to some of the future questions. So do whatever works best for you. Now, one thing I do want to mention before we move on is you'll notice that some of these questions have 5 choices while others have 4 choices. I don't know if this was seen in some of the other problem set questions, but the 5 choice questions are more AP level type questions, while the 4 choice ones tend to be from the Regents. Um, Remember the Regents questions, I tend to try to, I want to give you a nice variety of different ways to practice dealing with the questions. Try to build that foundation so that we can work on and do more complex force questions. All right. So I'll work on all these questions. We'll start with the first one. So pause video, work yourself, and go in a second. All right. So one thing to keep in mind is, and I'll say this in class, but one thing to keep in mind is that with all these topics, now that we're entering into a new unit, one thing to remember is that all the topics are connected in what I call a web of connections. What I mean by that is that each topic has different things that they talk about, like kinematics talked about position, velocity, acceleration, things like that, vectors, and dynamics has its own set, like forces and stuff. Now, one thing to note is that some of these connections connect with other topics. For example, the concept of acceleration pops up both in the kinematics unit and in the forces unit. Now, why is this important? Because the question asks, what is the speed at the end of the 6-second interval? Now, this is very clearly a kinematics question. In my mind, I'm thinking, okay, I'm going to have to do v equals v naught plus at for this. But the problem is I don't have the acceleration. I have everything else. I know it starts at rest. I know the time is for 6 seconds. The problem is I just don't have the acceleration term. So if I remember that acceleration is essentially the connection between dynamics and kinematics, what I can do is I can look at this 15 Newton force and remember I have an equation that connects forces to acceleration using the equation F net equals ma. So now I know how I go in this problem. I have to first start with F net equals ma. There's only a 15 Newton force, 15 newtons applied to a 12 kilogram object. It's going to produce some sort of acceleration. Divide both sides by 12. This ends up being, I don't have a calculator on hand, but about 5/4. Then this number can get plugged into here. And now I have my acceleration that I can then use to find the final velocity, and we should end up getting 7.5 for this. All right. We'll move on to question 2. So pause the video, work yourself, and we'll go in a second. All right. This one's pretty straightforward. They want the acceleration due to gravity. That's g. They give us the weight, which is fg. So we're going to use fg equals mg. And we're going to do 45 equals 15 times g. Divide both sides by 15, and we get 3 meters per second squared. All right. Now work on question 3. So pause the video, work yourself, and we'll go in a second. All right. So for question 3, once again, they give us this kind of information. They give us a lot of stuff, and they want us to figure out how far it goes. So this is another one of those cases where I have to start off with F net equals ma, find the acceleration, and then use that acceleration to find the answer. Now, the one thing that's a little bit weird is that in order to use F net equals ma, I need a mass, right? So F net equals ma, the force that it's hitting with, and we have to be very careful because it's not just any force. This is the net force being acted on this object. So this ball is being applied a 5 Newton force. Now, what about this 1 Newton force? Well, that's actually being used to give you the weight of the object, Fg, which then tells us that the mass is 0.1 kilograms. One of the things I mentioned before is that you want to get into this habit where the moment you see the mass, you immediately think about what the weight is and vice versa. So if you're given a weight, you immediately write down what the mass is. if you're given the mass, you immediately write down the weight is, because there's a good chance that you're going to have to do that at some point. And remember, it's only a factor of 10. So the mass ends up being 0.1, which means that the acceleration the object experiences should be about 50. With this acceleration, we are looking for the distance, so we're going to use the annoying x equation. Now, the first two terms all kind of just drop to 0, so I don't care about them. I only care about the second part, the third part. So 1/2 50 times 2 squared. This all gets us 100. Right. So again, it goes back to that idea that we're using a bunch of these different equations. This one was technically a three equation question where we had to find a lot of information before we get our final answer here. Now, if you don't see this right away, the way that you want to approach these problems is sort of working backwards. So they want to know how far the ball travels. Now, of the equations we have, so far we have, I think it's 5 different equations. We have 3 kinematics equations and then 2 forces equations. Technically, those 2 force equations are kind of the same thing. But the thing is, only one of them deals with distance and time, and that's the annoying x equation. With the only thing that I'm missing is the acceleration. So then I take a step back and say, without using the distance and time, how can I find the acceleration? Well, they told me force, so F then equals ma. But then I don't have a mass. So I take one step back and think, well, what equation can I use to find mass? It's not F then equals ma because that's the one I want to use. So what other equation has mass? And that leads me to Fg equals mg. So keeping this kind of methodology when you approach these problems and almost working yourself backwards and asking yourself, okay, what information am I missing to proceed with this equation? And then trying to find a new equation to work can really help with some of these more complex questions. Like I said, not every question is going to require multiple steps, but when they do require multiple steps, this is how you're going to go about it. All right, now work on question 4. Pause video, work self, and we'll go in a second. All right, so here, this is another one where they say the gravitational field strength. This is, again, just another word for G. So G stands for both the acceleration due to gravity, but also the gravitational field strength. Now, this is more common phrasing for the regions physics. I think I might say this when we actually get to Unit 3, where we focus a little bit more on the big gravitational force equation. But this is just another way of them saying that we're looking for little g. So we're going to use Fg equals mg because, again, only equation that has little g in it. We plug into the numbers, 350 and 70. And then we get that the answer is 5. Again, this unit is the same thing as meters per second squared. So they're interchangeable. All right, here's the next one. Pause video, work stuff. We'll go in a second. All right, so they want us to figure out what's going on with the motion of this object. Now, the first 2 choices says move at constant speed. These two, for the most part, are indistinguishable. If an object has balanced forces, because the only time that an object will be moving with constant speed is if all the forces are balanced, I cannot tell the direction that it's moving unless I'm given more information. I'll talk about that in a later topic in this unit, but for the most part, if you're given something generic like this, where all the forces do happen to be balanced, so you have 10 going to the left and then 10 going to the right, I can't tell what direction it's moving. It could be moving in either direction. I could know that it might be moving at a constant speed, but not what specific direction, not without a little bit more information. So A and B actually can be thrown out of this question for 2 reasons. One, because of the fact that the forces aren't balanced and the object's not in equilibrium, but also for the reason that they're not unique choices. Because technically, even if both of these were 100 newtons, I wouldn't have been able to answer this question as is. So the only other choices are whether it's going to accelerate to the left or right. Well, because the net force is going in the direction to the left, the direction where the higher force is, 120 to the left, 100 to the right, that means the acceleration also goes in this direction. One of the nice things about the equation F net equals ma is that it actually tells us that the net force and the acceleration always point in the same direction. So I'll explain it in class why that might be the case, or if you're curious, I'll answer that in class. But just keep that in mind that the net force and acceleration are always in the same direction. So the net force would be going to the left, therefore it's going to accelerate to the left. All right, here's the next one. Pause the video, work self, I'm going in a second. All right, so here they give us a bunch of information. They want us to figure out how much force is being applied to this object. So now this is kind of like the other 5-choice questions, the other AP style questions, but going in reverse. So this time we're going to start with the kinematics equations, because in order to find the force, obviously the only equation we can use is F net equals ma. But oh no, I'm missing the acceleration. So before I can continue finding the acceleration, I have to do one of my kinematics equations. They give us the distance, the initial and final speeds, and the only equation, and I'm looking for acceleration. So the only equation that comes to mind would be the timeless equation. V squared equals V naught squared plus 2a delta x. It comes to a stop. It's initially starting at 40 meters per second. We square that, 2a, and then it comes to a stop over 10 meters. So solving this, we end up getting whatever 40 squared divided by 20 is. So I plug this in for the acceleration. And what we end up getting is choice D, 3,200 newtons. All right. Question 7. Pause the video, work yourself. I'll go in a second. All right. So they want to know which object or which situation represents an object in equilibrium. There are two things that an object in equilibrium can be doing. They can either be moving in a straight line with constant speed or being at rest. This one, an object driving around a corner, that is not constant velocity or not in a straight line. So D's out. Gaining speed, well, that's a changing speed, so obviously not right. Woman accelerating upward in an elevator, well, it's accelerating, so that's not, that means changing speed and velocity. So the only one that fits would be choice B, standing still on a bathroom scale. All right. Here's the next one. Pause the video yourself. I'm going to go in a second. All right. Here. Now, what you want to do is look at all the forces acting on the object. Now, at the highest point, there's only one force acting on it, and that is the force of gravity pulling it down. And remember, the force of gravity is also called the weight of the object. So the net force acting on the ball is the weight of the object because there's no other forces acting on it. So the answer was D, same as the magnitude of the rock's weight. One of the things that makes this specific question difficult sometimes is for a few reasons. One, a lot of people tend to think that because the object is at its highest point, because the speed drops to 0 at that point, that means that the object is at rest and therefore at equilibrium, so the net force is 0. Both the Regents and the AP will tend to bank on this reaction in order to get you to accidentally choose it. So sometimes they may even throw in that part of the object at its highest point has 0 velocity. What is the net force? And they want you to think, oh, 0 velocity means at rest and net force is 0. Don't get into that habit. Think about all the forces acting on it. Try not to immediately think that, because again, it's going to lead you down to the wrong answer. So just go through all the forces. There's no normal force, there's no tension, there's no friction, there's nothing else, no applied force. The only force is the force of gravity going down, which is also called the weight. All right. Here's the next one. Pause the video, work yourself. I'm going in a second. All right. They want us to know which interval is the velocity constant. This is another way of saying that the object's in equilibrium and that the forces are balanced. So the net force has to be equal to 0. So the only time when the net force is equal to 0 is right here between 3 and 4 seconds. Question 10. So pause video, work yourself. I'm going in a second. So let's see. Now this is there's two things about this. First off, this is one of those scenario 1, scenario 2 questions. So they give us an acceleration and a mass, and then they say the same force is being applied to a different mass. There's a few ways of going about this. One way is to do the typical scenario 1, scenario 2, where you do the equation F net equals ma. We plug in scenario 1's information, say 4 times 3, to get that the net force acting on the objects is 12. And then we could say that that same 12 newtons applies to the 2 kilogram object, giving us an acceleration of 6. The thing I could do is what I could say that I can use the equation F net equals ma and realize that the force is constant. Therefore, I'm going to say that it doesn't change. It's just 1. And then I could see that mass and acceleration have an inverse relationship. That in order to keep the left side of the equation the same, mass, when it goes, the mass is decreasing. So when it goes down, I could tell that the acceleration has to go up. And the factor that the mass changes by is the same factor that the acceleration changes by in the other direction. So if mass is being halved or being divided by 2, decreased by a factor of 2, the acceleration has to be doubled. If you don't like this, don't worry. You don't have to do it because again, you can do it this way, the way I showed it on the left side, where you just calculate the stuff. Sometimes if they don't give you a number, you can always put in a number and do the calculations that way. Doesn't matter, but this is just a nice, easy way of saying, okay, I know mass and acceleration have this inverse relationship. So if mass is doubled, if the mass is being halved, then the acceleration has to be doubled. So if you can figure out how to do that and make it make sense to you and not make mistakes with it, you can easily get that question correct in much faster amount of time than doing it the long way. All right, here's the next one. Pause video work itself. We'll go in a second. All right. So they want us to figure out the acceleration due to gravity. Based off of this is Fg equals mg. Now, personally, I don't like using the equation. So if I just think about, what do I get if I do Fg divided by mass or slope? Turns out I get g. So the slope of this line will end up getting me the value of g. So 16 minus 0 divided by 10 minus 0 gets me choice D, 1.6. Okay. Here's the next one. Pause the video or cell phone. Go in a second. All right. Greatest inertia. That's just a fancy way of saying mass. So one with the greatest mass is this one, choice C. I mentioned before that a lot of times you'll notice is that the object with the greatest mass will usually have the worst speed. So that's pretty much going to be a constant thing that you'll see. And that usually plays into the fact that it's trying to confuse you with momentum, which you haven't learned yet, so it shouldn't be an issue right now. All right, question 13. Pause video with cell phone. Go in a second. All right. So they say, which of the following is not true about a 500 Newton box hanging on a massless rope in static equilibrium? So if an object is hanging from a massless rope and it's 500 newtons, there's a few things that we know. We do know that if the object is in static equilibrium, that's just another way of saying that the forces are balanced. So the net vertical force is 0. That is true. So that one's not going to be in. The net force being 0, that is also true. The tension in the rope is 500 newtons. That pretty much makes sense because if the weight of the box is 500 newtons, then the tension in the rope should also be 500 newtons. Now, we do have to be careful because they weren't explicitly clear on how the box is hanging, but based on the information, I can kind of assume that it's going to be directly ahead and not off at a weird angle. So this one looks like it could be wrong. The net acceleration 0. Well, if the net force is 0, the acceleration would also have to be 0. So the only one left would be the net horizontal force is 500 newtons. Yeah, that doesn't make sense. If the object is in equilibrium, the net force in both directions should be equal to 0. All right. All right. Here's the next one. Pause video, work cell phone. Go in a second. All right. So they say which of the objects is in equilibrium. This is another way of saying that the acceleration equals to 0. This doesn't make sense. This is an accelerating object. This is an accelerating object. So the only one would look like this. Remember, the curved, linear, constant, and 0. That if there is an if the acceleration is 0, then the velocity has to be constant. which means that my displacement graph needs to be linear. All right. And here's the last one. Pause the video over cell phone, go over a second. All right. So here we go. This one actually is finally kind of a tricky question, but it is interesting to see how it works out. And we're going to go through these types of questions. So if you had trouble with it, that's fine. We'll go over it. Now, first step in doing these problems is to draw FBDs. We're looking for this tension. I don't know what this tension is. So what I'm going to do is I'm going to call this T1 and this one T2 because we have two different tensions and I need to make sure I differentiate which tension's which. And then I have a force of gravity pulling down. Because this is a 30 kilogram object, I know that this is going to be 300 newtons. Oh, and I also know that this is at 30 degrees. Now, one thing that I need to do is once you draw an FBD, you then have to redraw it, breaking up any forces that are at weird angles, right? Just like how we talked about when we did those projectiles, that you can't be dealing with projectiles with velocities at angles. We can't do with forces at angles. So we have these two forces again, because they act in the horizontal and vertical purely directions. What I'm going to do is T2 goes off at an angle like this. That means it has a leftward component and an upward component. The leftward component would just be T2 cosine 30, and the vertical component would be T2 sine 30. I apologize because I don't have the calculator on hand. I don't remember what these are in fractions. I know that this one's going to end up being 1/2 T2. I don't know about this one though, so sorry for that. But what I'm going to do is I'm going to replace this upwards angled T2 with the vertical component, which is 1/2 of T2, and this horizontal component, which is T2 cosine 30. All right. So what I can do is say, use my equilibrium forces questions. In the y direction, because it's in equilibrium, I know the forces in the y direction equal 0. So 30 newtons minus 1/2 T2 equals 0. So moving things around, I end up getting that 30 equals 1/2 of T2, or that T2 equals 60 newtons. By breaking these up into components, I can tell which part of T2, the component, the vertical component, has to be equal to 30 in order to balance it out. Because again, it's in equilibrium. So I know that the forces in the y direction and the forces in the x direction are both equal to 0. So I could do the same thing. I set these two equal to each other. Now it doesn't matter which one I say is positive and negative because it doesn't really matter in this context since it's going to be equal to 0 anyway. So I could say the right is positive or the left is positive. It doesn't really matter. So solving this, I get that T1 is equal to T2 times cosine of 30. I already figured out that T2 is 60 newtons. Oh, sorry. I just realized I made a mistake. That's 300, 300, 600, 300, 600. I apologize. So 600 cosine 30 degrees, which gets me the answer 520. I knew something wasn't making much sense. 520. Right? Like I said, this one's a pretty tricky question. Now, there actually was a faster way of doing this, but I didn't want to really spoil that. But the whole idea still comes from the fact that this is the typical setup that you want to approach with a lot of these force problems. You want to start off with drawing an FBD, like right here, then break up any forces into their x and y components using SOHCAHTOA. Again, y components are always sine, x components would be cosine, as long as the angle is next to a horizontal line, like here and here. Then what you do is you use your force equations, either F net equals ma or F net equals 0, if depending on whether the object's in equilibrium or not. And then you just plug in the numbers and then follow through. We're going to be doing a whole lot more of these practice problems in class over the next few days. So if you're kind of still a little confused about it, Don't fret, we will be doing more of these later on. All right. If you have any other questions, feel free to let me know. Otherwise, good luck and have a great day.